This is part 6 of the Module 10 lecture. Again, I wanted to re-explain this table because I feel that in the previous recording I didn't go through this very carefully. All right, so in here, this is the example for testing independence. So what the software is showing you is the contingency table, but now it's showing you 3 entries for each cell. The first entry is the observed frequency. The second entry in that cell is the expected frequency. And the third value is the cell chi-square value. In here, the rows, of course, is the income levels. Here are shown as numbers. And then at the top, they're showing you the time between visits to the physicians. Then you have the total marginals, and then the row marginals. And then the value of the test statistic, this chi-square, is 47.892, which is obtained by summing all the individual chi-squares for all cells. This is telling you this has 8 degrees of freedom, and it gives you the p-value. Software packages, they do not work with the critical values. They only show you p-values. Again, typical, when I do this with software, I present this to the students and I ask them to interpret the results. Of course, they are familiar with how to produce this using software, and they know what these entries are. All right, so again, I'll leave it there. We're not going to be doing this because we're not using software in this class to solve these problems. So let's move on to the test of homogeneity. So the procedure to conduct the test of homogeneity is exactly the same as the procedure to conduct a test of independence, with the 2 exceptions. Number 1, how we state the null and alternative hypothesis, and number 2, how we interpret the decision about the null hypothesis. All right, let's look at an example to see how we did this. So in this example, this is a study that assesses the characteristics of the students that attended a 5-day human sexuality program. And in this, you see that we have the categories of the types of subjects. We have medical students, nursing students, other types of students, and group leaders. And then we have 2 populations, those that are single and those that are married or divorced. And as the question says, at this significance level of 0.1, we want to determine if students are uniformly distributed by their marital status. So we want to see if the proportion of each type of student that is single is similar to the ratio of the students that are married or divorced. So in here, we have a test of homogeneity. We want to see if there is a homogeneity in the proportions of single students as compared to married or divorced students. All right, so the first step is to state the null and alternative hypothesis. So the null hypothesis is that the proportions of subjects in the course are the same with respect to their marital status. And the alternative hypothesis is that the proportions are not the proportions of the subjects attending the course are not the same with respect to their marital status. And of course, how you state the null and alternative hypothesis comes directly from the statement of the problem. Again, this is a right-tailed test. It's the only choice we have. And the significance level in this case is 0.1. Now, the distribution to use, we have a 4x2 contingency table. We have 4 types of students and 2 marital status. And then, this contingency table has discrete categories and discrete the frequencies come from discrete counts. All right, so if the expected values are at least 5, then we will be justifying using a chi-square distribution with 3 degrees of freedom. 3 because the number of rows is 4 minus 1 is 3, times the number of columns, which is 2 minus 1 is 1, and that's why we end up with 3 degrees of freedom. All right, in this table, I'm showing you how we calculate the expected values, which is we multiply the marginal frequencies of the rows times the marginal frequencies of the columns, like 70 times 69, and divide that by the total frequency, 143. That gives you the expected value for the first cell. For the second cell, we have the row total is 70 times the column total 69, or you can say the row marginal frequency times the column marginal frequency. So it's 70, I'm sorry, for the second one is 70 times 74 divided by 143 gives you the second expected value. Then you go on to the next row, row 2, column 1, and again you multiply 37, because we're now in the second row, times the total of the first column divided by 143, and that gives you this number, 17.853. So you continue that until you get to the last row. And so in this table, I'm showing you all the expected values for all the cells. And you can see that in every case, the expected count is more than 5. So yes, we can use the chi-square distribution with 3 degrees of freedom. All right, so now this is the second step. In the third step, we calculate the test statistic. So again, it's a good idea to have the table with the observed frequencies and expected frequencies, so that we can calculate each of the components of the chi-square statistic. So for the first cell, we use the observed frequency, which is 50 minus expected frequency, which is 33.776. We squared that and we divide that by 33.76, expected frequency. So that gives you the chi-square for the cell 1, the cell 1, I should say. Then for the cell 1, 2, then you do 20, which is the observed frequency, minus 36.224, which is the expected frequency, squared divided by that expected frequency. And you can see, you can continue then here the calculation for the second row, first column, and second row, second column, and all the way to the last row and column. So you calculate all these 8 chi-square components of the overall chi-square of the test statistic, and you end up with 35.761. So once you have the test statistic calculated, then we determine in step 4, either if you use the critical value approach or if you use the p-value approach. If you decide to use that critical value approach, or you've been asked to use the critical value approach, then remember this is a right tail test, so the rejection region is in the right tail of the chi-square distribution with 3 degrees of freedom. To find the critical value, you go into table 6, look at the row for 3 degrees of freedom, and then look at the probability of 0.1. At the intersection of that row and that column, you find the critical value of 6.251. So the rejection region is for any chi-square value larger than 6.251. All right, if you are asked to use a p-value approach, then you use the calculated value of the test statistic, 35.761, and then you look at the row for 3 degrees of freedom on table 3 and see where that value is with respect to the values listed on that row. And you will see that the largest value in that row is 12.838. So when you look at that row of 3 degrees of freedom in table 6. And that value, 12.838, corresponds to a probability of 0.05. And because the chi-square, the test statistic is larger than that, well, that's telling you then that the probability, that is the p-value, is going to be smaller than 0.005. If you like to find the exact p-value, then you use this formula in Excel, and then you find that this is a 0.00000084. Very, very small. All right, so now that we have that information, we can go on and make a decision about the null hypothesis. So the calculated value of the test statistic is 35.761, which is much larger than the critical value of 6.251. So that is telling you that the test statistic is in the rejection region. Also, we found that the p-value is smaller than 0.05. So both approaches tell you that we should reject the null hypothesis that the proportions of subjects in the course are the same with respect to their marital status. So we reject that. And therefore, the interpretation of our decision is that at a significance level of 0.1, we conclude that the proportion of subjects attending the course in the 5-day human sexuality program are not the same with respect to the marital status. And as before, we know that the proportions are not the same. And of course, that begs the question, well, which categories are not equal among the married and divorced and the single students? Well, you can do a qualitative analysis using graphs in Excel, where you can compare the chi-square values, and you see that the larger chi-square contributions come from the medical students, both the single and married and divorced, and for the leaders also married and divorced. So these are the four bigger components of the chi-square. Now, if you look at that difference between the observed minus expected, then you see that for single medical students, this is a positive value, meaning that there's more students that came to the course than expected that were single, and there were less students that were married than expected. In terms of the leaders, you can see that for single, this is a negative value. That means that the expected value is larger than the observed. So there were less leaders that were single that came to the class than expected as compared to those that were married and divorced. So leaders typically are older people that more likely are married. So there is expected that will be more married leaders than they will be single. The same with the medical students. Very likely the majority of them are single because they're in school as compared to those that are married. So again, this helps you provide a little more analysis about this conclusion. And as I mentioned in the previous recording, when it comes to an exam, I will ask you only to interpret the decision. I will not ask you to go into these details. I'm providing this for you because I don't know about you, but once I see this, I'm very curious and I would like to say, well, where is the difference coming from? So this is what this is attempting to tell you, why the null hypothesis was rejected and where the proportions are not similar. All right, I will stop here, and then in the next recording, we'll talk about the inference about a single population variance.